If you grew up watching classic cartoons, you probably had the same childhood wish I did. We all wanted a magic carpet that could glide smoothly and silently through the sky. But bringing that into the real world hits a massive mathematical wall. Structurally, a flat, flexible piece of fabric is destined to fall out of the sky the moment it encounters the wind. The teardrop shape of an airplane wing generates clean, upward lift arrows. Compare that to a flat rug. The fabric creates chaotic drag vectors coring it downward. Forced forward without a tail or rudder, that flat shape tumbles uncontrollably through the air. Turning that childhood sketch into a functional aircraft meant abandoning the fabric and starting with a rigid, lightweight frame capable of housing high-speed electronics. The result is a design that actually flies. Stabilizing a flying carpet means overcoming 3 specific aerodynamic challenges: lift, torque, and balance. When you think about making a rectangle hover today, the most obvious solution is to just attach 4 downward-facing drone motors to the corners of a rug. This diagram shows a 3D wireframe of a quadcopter layout beneath a solid flat plane to explain a concept called downwash. Downwash is the downward deflection of an airstream by an aerodynamic surface. When you put a large solid carpet directly above lifting propellers, those downward thrust arrows bounce directly back up into the plane, creating massive red canceling drag arrows. The net mathematical result is that the upward lift force is neutralized by the downward drag hitting the fabric. You get 0 flight. To solve this, the engineering has to pivot. You have to abandon vertical drone lift entirely and use horizontal forward thrust, treating the carpet like a traditional fixed-wing glider. The team built a new architecture. They stiffened the carpet using ultralight styrofoam, the tight, rigid kind used to build RC planes, and mounted 2 high-powered motors at the rear to push it forward. True flight requires shaping thrust to work with the surrounding air, rather than fighting against your own surface area. Securing 2 massive motors to the back of a styrofoam board introduces the next invisible enemy on the test bench, the rotational physics of torque. Torque is the twisting force that causes rotation around an axis. This schematic shows the rigid carpet from the rear. If both of these high-speed motors spin clockwise, they generate a massive circular torque arrow. That rotational force causes the entire board to violently barrel roll in the opposite direction. The mechanical fix is to reverse one motor so it spins counterclockwise. These 2 opposing rotational forces collide and cancel each other out perfectly, creating a stable platform. That keeps the board flat, but we still have a steering problem. A flying rectangle has no traditional tail or rudder to keep it pointing straight. The solution is a delta wing setup managed by an electronic flight controller. A flight controller is a tiny onboard computer that constantly computes sensor data to automatically adjust artificial stability in real time. By cutting 2 small flaps at the rear of the board, the flight controller can precisely manipulate the passing airflow, allowing the craft to pitch up and pitch down or roll side to side. When an object lacks natural aerodynamic stability, computational control and careful counterforces must act as the invisible hand keeping it level. Even with the motors perfectly tuned, the first test flights often fail. The carpet immediately pitches its nose up, stalls out midair, and crashes straight back into the dirt. An incorrect center of gravity caused the crash. With a heavy battery near the back, the tail drops, the nose points up, and forward velocity stalls. Relocating the battery to the front shifts the fulcrum point forward, forcing the nose down into a level glide. With the thrust engaged, the torque perfectly balanced, and the center of gravity finally dialed in, it works. Watching this rigid board skim across a green field is surreal. It looks exactly like the childhood cartoon fantasy brought into the physical world. By breaking down a mythical concept into a series of solvable engineering problems, physics can replicate the behavior of a childhood fantasy.